In this video, we're going to talk about change of variables. Let's start with the definition. The Jacobian, which we're going to write capital J, xy to uv, is a determinant. Specifically, it's the 2 by 2 determinant. In the top row, it looks like x sub u, x sub v, and in the bottom row, y sub u, y sub v. So these are all partial derivatives inside this determinant. This Jacobian is often written delta of xy over delta of uv. So you'll see that notation in some textbooks, but I think this notation here, where we have the xy to uv in the subscript, is the most helpful when we're talking about changing variables in a double or triple integral. So let's find j sub xy to r theta for x equal r cos theta and y equal r sine theta. So essentially what we're doing here, we're moving into polar coordinates and we're going to investigate this Jacobian. So here's how to calculate the Jacobian, xy to r theta. By definition, it's going to be a little 2 by 2 determinant. We're going to look at our first variable x and we're going to take partial derivatives of that with respect to the second set of variables. So x sub r, x sub theta. And then in the bottom row, we look at our second variable y and take partials with respect to the second set of variables. So let's write down these partial derivatives and then we can calculate the determinant. So in the top row, taking the partials of x with respect to r, cos theta, and partial of x with respect to theta, negative r sine theta. Okay, and then we do the same thing for y in the bottom row, sine theta and r cos theta. And then we're just calculating this 2 by 2 determinant in the usual way. So multiplying these guys and then subtracting off that product there. So we'd have r cos squared theta, and then we'd have minus a negative term. So I'm going to write plus r sine squared theta. All right, so we can factor out the r, have r times cos squared theta plus sine squared theta. Stuff in the brackets is going to give us 1. So there we go, we've calculated our first Jacobian and it comes out to r. So this is no coincidence that r is the correction factor when we move from xy coordinates into polar coordinates. This is what the Jacobian is doing. In fact, the absolute value of the Jacobian is giving us the correction factor when we change variables. So let's make that specific by writing down a fact. Here's our formula for change of variables. So if we want to integrate a certain function with respect to x and y over a region R, sometimes we'll find it easier to change variables. So if we want to do that, changing over to variables u and v, we rewrite our function here in terms of u and v. Differentials become du dv, but we need this correction factor on here. This is the absolute value of the Jacobian. Otherwise known as your correction factor. So we're doing the double integral over the same region R, integrating the same function, changing the variables, and as we change these variables here, space gets distorted, and the absolute value of the Jacobian gives us a correction factor for exactly how space gets distorted. Here's another fact to help us with our change of variables. Sometimes this Jacobian that we're looking for, Jacobian from xy to uv, is a little tricky to calculate directly. And it turns out that that Jacobian is the same thing as 1 over a different Jacobian, specifically the Jacobian when you're doing the reverse change of variables, so from uv to xy. So Jacobian from xy to uv is actually just the reciprocal of the Jacobian from uv to xy. And that works out really nicely when this Jacobian here that we've got on the right side, sometimes that one's a little easier to calculate. So I'm going to rewrite this fact using the delta notation for Jacobians, just in case you prefer that notation. So remember we said the alternative notation for Jacobians is you could write delta of xy over delta of uv, and we're saying that another way to calculate that is to take the reciprocal of a different Jacobian where in fact you're starting with your variables u, v, and then you're moving over to variables x, y. So that's just an equivalent way of writing that. So let's evaluate the double integral over region R of y squared dx dy using a change of variables. And we've got a description of what our region R looks like. It's the first quadrant region bounded by 4 different curves. So I'm going to break this type of problem up into steps. First thing we're going to do is we're going to rewrite our region R. So let's look at these boundary curves here. 2 of the curves involve x, y equals something. So these curves would become a lot simpler if we just renamed x, y. Let's call that u, for example. So if we said u is equal to x, y, then our curves become u equal 2, u equal 3. So that certainly looks a lot nicer. And then for these lines here, this y equal x and y equal 4x, well, we could rephrase this one as y over x equals 1. And we could rephrase this one as y over x equals 4. So we could introduce a new variable, let's say v, called y over x. And then we could say, okay, now our curves become v equal 1 and v equal 4. So the idea is to introduce a couple of new variables so that your boundary curves become u equal constant and v equal constant. So now we can say our entire region R is now just ranging from u values 2 to 3 and v values 1 to 4. Okay, let's draw a picture of this region so we can see that visually. So quick picture, we're just talking about the first quadrant region. xy equal 2 and xy equal 3 are hyperbolas. So let's say they look a little something like that. And then we've got the line y equal x and the line y equal 4x. So just very rough sketch says that our region R looks something like that. It would be challenging to do a double integral in coordinates xy over that region. You'd need to split that up into several integrals. But if we switch variables and we just say, okay, u equals xy, v equals y over x, then we suddenly have these really nice limits of integration for u and v. That's going to make the calculation nice and easy and no need to split up into multiple integrals. So in step 1, we decided what our new variables would be based on looking at our boundary curves, and we rewrote our region R. So now our goal is to rewrite the integrand. So let's scroll back to the problem for a second so we remember what the integrand was. It was y squared. So we want to rewrite y squared using these new variables u and v that we figured out. And typically this is going to involve a basic arithmetic operation like maybe adding your variables together, subtracting, maybe dividing or multiplying. So let's see what we could do. If we were to multiply u and v together, the x on top would cancel with the x on the bottom and we just have y squared. So in other words, y squared is the same thing as u times v. And so we have rewritten our integrand into our new language. In step 3, this is where we're going to find our correction factor. And specifically our correction factor as we move from xy to uv is going to be the absolute value of a certain Jacobian. And in the subscript, we just write what variables we're starting with, xy, and what variables we're going to. That's going over to uv. Now it turns out that it's going to be easier to calculate the other Jacobian first. So we're going to start by calculating the Jacobian from uv to xy. And just by definition, let's think about what that is. So that's a 2 by 2 determinant. If you look at your very first variable here, u, you want to take partials of that variable with respect to the second set of variables. And in the second row, you work with your second variable v and take partials of that with respect to your second set of variables. Okay, and then let's just flash back to what we said above. I think I'll write something near the top of the screen here, just reminding us what we said our u and v are so that we don't have to keep scrolling. So we said u was xy and v was y over x. Okay, perfect. So we'll have that to look at as we compute these partial derivatives. So we're talking about the 2 by 2 determinant. Taking partials of u with respect to x, we'd have y, and with respect to y, it would be x. and then we move on to our variable v, which is y over x, taking our partials, minus y over x squared, and then 1 over x. Okay, and so now we're going to compute this 2 by 2 determinant in the usual way. Just multiply these guys, subtract off the product of those guys, and we get y over x minus a negative y over x squared times an x. Okay, so basically what's happening here, y over x plus another y over x, in other words, 2 times y over x. Okay, now what we're trying to accomplish in this problem is switching the whole double integral over to the new coordinates, u and v. So rather than leaving this as 2 times y over x, we really want to get this back in the language of u and v. So let's scroll back for a second to our variables. Remember that v was y over x. So a better way to say this would be to say that's 2 times v. Okay, now this is not exactly the Jacobian that we're looking for in the problem, because in this problem we're actually moving from variables x, y to variables u and v. But this Jacobian is the reciprocal of the Jacobian that we're looking for. So we can say Jacobian from xy to uv in general is going to be 1 over the other Jacobian going from uv to xy. And so we can say that the Jacobian we're looking for is 1 over 2v. The last adjustment we need to make here is we need to make sure that we're taking the absolute value of the Jacobian. So your correction factor is always going to be non-negative, but for now we just need to remember to take the absolute value of that. And we can look back at the problem and we can say, well, what were the range of v values that we were working with in this problem? Let's scroll back for a second. We said that v was going to range from 1 to 4. So we know that v is a positive number here. Therefore, we can say that the absolute value of our Jacobian is just 1 over 2v. So if v for some reason were a negative number, then you'd use the negative 1 over 2v, but in this case we're good to just use 1 over 2v. So that's our correction factor done, and with that we are ready to do step 4, which is the actual changing of the variables. I'll write down the formula in general and then we can see how it works in this case. So double integral over some region of some function with respect to x and y is going to be the double integral over that same region, same function, times a correction factor, which is the absolute value of the Jacobian. And just write down which way our variables are going. We're starting with xy and we're moving over to uv. And then we've got our du, dv at the back here. So in this case, what we're saying is the double integral over region R of our function y squared dx dy, that's what we're trying to compute, is going to be the double integral of that same function, but now rephrased using u and v. Okay, so we did that in step 2. Let's see, we said our integrand would be uv, so we can plug that in there. So our function is uv. We said our correction factor, which is the absolute value of the Jacobian, would be 1 over 2v. That gets integrated with respect to u and v. And then we can just look back at step 1 to see what the range of u and v values were. So step 1, let's see, we said u values were going to range between 2 and 3, whereas our v values were going to range between 1 and 4. So we can throw those limits of integration on there onto the appropriate integrals. So du tells us that u is going to belong to the inside integral, u values on there going from 2 to 3, and v values going from 1 to 4. So now we have a really nice double integral. The integrand is going to be easy enough to deal with, and the limits of integration are super friendly. So that's the point of changing variables, to take a region that was quite difficult to describe in variables x and y and create a double integral that's easy to compute. So let's try it. So to get this integration done, I would notice that a factor of v can cancel out from the top and the bottom of that integrand. So we're really just integrating u over 2 then. And let's start with our inside integral here. So we'll leave our outside integral and our dv on there. Integrating u over 2, we'd have u squared over 4, and that needs to get evaluated at u equal 3 and u equal 2. Okay, so that gives us 9/4. Actually, I might write the 1/4 out in front just to make life easier. So 1/4 is going to come up in both these expressions, and then we got 9 minus 4. So in other words, just 5 as our integrand there, and then that's going to be times dv. Okay, so what that's looking like then is 5/4 times the integral from 1 to 4 dv. Anytime you're integrating just a differential, you just get the length of that interval because you're going to integrate this to get v, and then that will get evaluated at 4 and 1. So that integral is just going to be 4 minus 1, which is 3, and that gives us our final answer for our double integral, 15 over 4. Let's talk a little bit about the geometry of what the Jacobian was doing for us as we switched variables. So I'm going to draw a picture of the region that we had in our previous problem. So we had two hyperbolas, so xy equal 2 and xy equal 3, look roughly like that. And then we had this line y equal x, and then another line y equal 4x. So we're just talking about the first quadrant region bounded by all those curves. So that was our region R there. We decided in our problem that it was going to be better to substitute u equal xy and v equal y over x, because that way then we could describe our region as ranging from u going from 2 to 3 and v going from 1 to 4. So if we do that and we draw that geometrically, then we could say, okay, now we have these new variables, u and v, and we're now integrating over a rectangular region. So we want u to range from 2 to 3 and v to range from 1 to 4. So just capturing this nice rectangular region, which is now easy to integrate over. So let's say our problem is to find the double integral of, let's say, dA over this region. Maybe we're just trying to find the area of this region R here. So we'll say that just to keep our discussion simple. Let's say we're trying to find this area. The issue that we're going to have is that this area R is not actually equal to the area of the red rectangle because space is being distorted as we move from xy variables to uv variables. So let's make this idea a little bit more specific. Let's say you take a little tiny rectangle in your first region R, and the area of that rectangle, we're going to call that dA. So dA is just our dx by dy. Now, if we were to look at all the points in that little rectangle, figure out what x value and y values are being captured in that little rectangle, and then we change variables over to u and v, and we figure out, okay, what points u and v is that little rectangle corresponding to? In the uv plane, those points are no longer a rectangle. So they're probably a distorted shape. Who knows exactly what the shape will be, but not a rectangle anymore. And the area will not be the same as the area dA that we started with over here. And it actually gets a bit more complicated than that, because you could say, okay, this little area here, let's say maybe it's 3 times the area of dA. Well, it could be that when we look at a different chunk of our region R, let's say we look at this rectangle, it could be that this rectangle needs a different correction factor than the first rectangle did. So maybe this second rectangle becomes this kind of shape here. So the shapes are being distorted and the areas change as we move from xy to uv. Not only that, but the areas don't change with a constant correction factor. The correction factor for the area might actually depend on the coordinates within our region R. So it might actually depend on our position within that region. Okay, so now let's bring the Jacobian into the discussion. So the Jacobian, if we talk about the absolute value of the Jacobian from uv to xy, that is the factor by which areas are scaled as we move from variables xy to uv. Now, when we compute our double integral, what we need to do is correct for this scaling that's happening. So we actually need to multiply by the reciprocal of this Jacobian. So we know that the Jacobian going the other way from xy to uv is the reciprocal of the Jacobian going from uv to xy. Because this is the reciprocal, then multiplying by the absolute value of this Jacobian here corrects for the scaling. And incidentally, we need the absolute value of the Jacobian just because we care about the multiple by which the scaling is happening. We don't care about whether our points are being reflected. They get mapped from xy to uv variables.